Okay, ladies and gentlemen, so welcome to the Monsoon Seminar this week. Our speaker today is Cristiano Chiess from the University of Sao Paulo in Brazil. This is a change of theme. He's going to be talking about South American climate and monsoons today. Cristiano is an associate professor in Sao Paulo. He did his PhD at the University of Bremen in Germany, where I was learning a few minutes ago. We overlapped when I was a Humboldt fellow there. And he has wide-ranging interests in paleoceanography, paleoclimatology in the Atlantic and in the neighboring continent. So Cristiano, please take it away. And if you have questions, ladies and gents, put them in the chat and I'll call on you at the end. Thank you.
Thank you very much, Peter. Thank you very much for the introduction. Welcome everyone to this week's seminar. It is a huge pleasure for me to participate on this fantastic series of seminars. The topic of my talk is the orbital and millennial scale changes in tropical South American precipitation. And hopefully I'll be able to point some causes and consequences of those changes. All right, I have to make an addition to the title, namely this short sentence, a view from the ocean. Basically, the data I will show you here come from marine sediment records. I will also show some continental records for the sake of comparison, and because some of them are classic records and very important to frame, let's say, the data I will show, but mainly we will have a view from the ocean about the topic of today's talk. And I'll start by the end, and namely pointing you these takeaway messages. They are four. Try to summarize everything within these 4 sentences. There is much more to come for sure, but I would like to start by reading these sentences, although it may be a little boring, but I think this will help us to digest the whole talk as we make progress. So first is that high austral summer insolation enhances convection and precipitation over Western Amazonia and the South Atlantic convergence zone. I'll show you later on what is the South Atlantic convergence zone for those of you who are not very familiar to the specific features of tropical South American climate. Second, that the same high austral summer insolation also triggers a contraction of the seasonal migration range of the intertropical convergence zone, at least over northeastern South America. So this is very much different from what has been there for 30 years in the literature. And I hope I can show you some evidence that this is the case. Third, that precipitation over northeastern Brazil, now more specifically, there is strongly controlled by the intertropical convergence zone, varied linearly and synchronously to past millennial scale changes in the Atlantic meridional heat transport. Please note that we now shifted to millennial scale changes. And fourth, that we see, or we don't see, any substantial changes in precipitation during Heinrich stadials over subtropical South America. We do see them in tropical South America, but we do not see them anymore in subtropical South America. And I hope I'll also be able to show you why this is the case and where we stop seeing an influence of millennial scale precip change events during millennial scale climate anomalies. All right. I divided this talk in 4 main sections. First, I'll show a few slides about modern tropical South American precipitation, just to be sure that we are on the same page and that I'm not describing some specific features like the South Atlantic convergence zone. And you may be asking, where is this feature placed and what is it actually? And then I'll go to the main topics, namely the orbital scale changes in tropical South American precip and millennial scale changes again in tropical South American precip. And I'll come back to the very same slide I showed you before, the takeaway messages, and I hope by then you'll be convinced that they hold, hopefully. Okay, before showing the main features of modern South American precipitation, I'd like to show you this this map from IPCC AR6. This is projection of precipitation change. This is a annual mean of 19 models, CMIP6 models used in IPCC AR6. And this is anomalies shown against climatology of 1850-1900. If we focus, there are plenty of features in this plot, but okay, yes, and very important, this is for a warming of 4 degrees C. This is SSP 5/8.5, right? And if we look into, we concentrate into tropical South America, you will see a lot of hatched areas where there is low model agreement. We have 19 models. Low model agreement means that we are unsure about what is happening in the future, what will happen in the future over tropical South America. This also happens in other places of the world, but the focus here is tropical South America. So the low model agreement opens the possibility or the necessity, if you want, the need of, in my opinion, robust data model validation exercises. Because these data model validation exercises, specifically for different than modern climate conditions, may help on the identification of the most skillful models among these, for instance, 19 models that I just showed you the ensemble before, and it's in this slide. Yeah, still. And why I'm mentioning data model validation exercises for different than modern climate? Because 2100 climate will most probably be substantially different from climatological climate we know from pre-industrial. Say 1850, 1900, 1950, from these 100 years that we have pretty well covered by instrumental records. And by allowing the identification of the most skillful models, this exercise will, in the best case, allow us to pick up the most probable scenarios, and on base of these most probable scenarios, we will be able to inform stakeholders and hopefully have appropriate adaptation measures applied. And yeah, but in order to perform data model validation for this different than modern climate conditions, they are past climate conditions, they are geologic, they are archived in geological archives. We need comprehensive reconstructions of past changes, in this case, in South American precipitation. And this is the topic of today's talk. Well, this is a annual mean precipitation map of the whole South American continent. We have areas receiving much more than 3,000 millimeters per year. We have areas receiving less than 500 millimeters per year, all of them in tropical South America. This will be the focus of our talk, as I mentioned before. And importantly, our focus will be on tropical South America to the east of the Andes. The Andes is this very long and up to 7,000 meters high mountain chain at the very westernmost edge of the continent. So we'll be focusing on tropical South America to the east of the Andes. A few climatic features are particularly relevant here, and two I would synthesize, if you want. The South American monsoon system that brings and is responsible for a lot of precip in the Western Amazon and also in the South Atlantic convergence zone, this northwest, southeast elongated band of high precipitation. And these are two typical precip diagrams for these two regions. This is Western Amazon, and this is the typical South Atlantic convergence zone site. You can see on both of them high precipitation values during austral summer, December, January, February, extending a little bit more in case of the Western Amazon. And this also happens here around 20 south, 45 west, where we have a typical bimodal precip diagram that is strongly related to the South American monsoon system. Obviously, total amount of precipitation in the Western Amazon is much higher than in the southeastern portion of Brazil, for instance, but they both show this typical pattern. And another feature that I must mention here is the influence of the intertropical convergence zone over precipitation, and the places over South America that are most sensitive and more clearly show a response to intertropical convergence zone is this area here shaded in brown. This I will call this northernmost South America. Cariaco Basin is a great example of an area affected by this system, and also northeastern Brazil or northeastern Brazil, this portion here. And here we have two typical precip diagrams. Again, this is climatology for northernmost South America. Here, peak in precip you can see is August, July, August, September usually. This is when the ITCZ is located furthest north over South America. On the other hand, in March, April, we have peak precip over northeastern Brazil. This is when ITCZ is positioned furthest south. All right, so let's move on to orbital scale changes. I would like you to focus, first of all, on this red record here in panel B. The record is going all the way back to 150,000 years, and this record comes from a core collected under the influence of the Amazon River discharge. What we are showing here is the amount of the proportion of Andean sediments versus the amount of lowland Amazonian sediments that end up in this site. How we came up with this proxy, if you want, we used major elements, analyzed it with an scanner XRF on this core, and we, through n-member modeling, based on modern fluvial samples of the major tributaries of the Amazon basin, we found an n-member that is typical, that synthesizes the Andean response, and we came up with an n-member that clearly is related to lowland input. What we can see is a variability on this record, and is an orbital scale variability. For instance, if we take here around 45,000 years before the present, we see a relative increase in the Andean proportion of sediments, and importantly, this increase is related to an increase in southern hemisphere. This is December, January, February insolation. So this is the axis of insolation, strongly, obviously, as you know, controlled by precession on this specific latitude and time of the year. This is not the case. This is not only the case for this peak, but for most of other peaks we have in this very beautiful and 250,000 years long record. On the bottom of the panel, we have three cave delta 18O carbonate records, all of them organized in such a way that upwards in the plot means more precipitation. And if we take, again, let's take now this example here, the transition from marine isotope stage 5 to 4. We have this beautiful peak in Andean sediments reaching the Western Atlantic Ocean. We have a positive anomaly in southern hemisphere summer precipitation, and we do have increased precipitation over these three sites. Where are they? Two of them, these two here, panel C and D in the Western Amazon, and the one bottommost, panel E, here, southern Brazil. So increased discharge of Andean sediments. This means more erosion over the Andean slope facing at the Amazon for sure. We also see more precipitation as expected in the Andes, and we also see increased precipitation over southern Brazil, much more related in this case to the South Atlantic Convergence Zone. We performed a time series analysis, different methods. This is just an example on the red curve I showed you before. Indeed, we have this strong precession periods here, 2319 Ka on that record. And this shows us that periods of higher austral summer insolation are related to enhanced precipitation over Western Amazonia. And why not? The Andes facing Amazonia, and also then high austral summer insolation enhances convection over Western Amazonia. This is due to the typical monsoon controlled by precession. Please note that we are on the southern hemisphere, and so this is in antiphase with the classic orbital scale variability of, for instance, Chinese monsoon records. If we now go to the south, but still sticking to tropical South America, I would like to raise your attention to this record in blue here. This is now the longest available record and for the late Quaternary of the changing strength of the South American monsoon system. It goes back 320,000 years before the present. And what we are showing blue here is the simple titanium to calcium ratio on this marine sediment core. Here's the orange or the yellow dot placed on the site this core was collected. Please remember that this is very much under the influence of the South Atlantic Convergence Zone, a main feature of the South American monsoon system. So, because we have titanium to calcium here, whenever values are higher, it means that we have more siliciclastic sediments reaching the core side, and the opposite is also true. We filtered this beautiful record, and with the precession filter, and when we compare either the raw blue data or the red curve to precession in the dashed line, panel A, or with the 20 degrees south insolation for December, January, February, again, we see this very beautiful and tight coupling of siliciclastic discharge in a region under the influence of the South Atlantic Convergence Zone and changes in insolation. And the phase is the same I showed you before, but this is a different place, different drainage basin, different proxy if you want, because there we used all elements from not all, but a suite of elements from X-ray scanner, here only titanium and calcium, the classic titanium and calcium approach. At the bottom, I'm keeping the Botuverá Cave Delta 18 record that I showed you before, just to show this in-phase changes happening here in the 20 south, but also a little bit southern than at 27 south. It's the location of this cave. Again, also time series analysis of the blue record I showed you before brings in high statistical confidence, a typical precession period. And this allows us to state that now periods of higher austral summer insolation, so far is the same as one of the slides I showed you before, are related to enhanced precipitation, and now over South Atlantic Convergence Zone. So not only westernmost Amazon, but this whole band of increased precipitation extending from Western Amazon all the way to the Atlantic in this northwest to southeast shape is affected by changes in insolation, southern hemisphere's summer insolation. And this same high austral summer insolation enhances convection over the South Atlantic Convergence Zone, on top of enhancing convection over the Western Amazon. Again, this is also due to the continent to ocean contrast in heating because of changes in summer insolation. All right, so far we have seen that changes in precipitation over Western Amazonia and the South Atlantic Convergence Zone are in phase with austral summer insolation. And this beautiful long records, 320,000 years of beautiful quasi-sinusoidal changes corroborate one such statement. But what about the region dominated by intertropical convergence zone? That region, northernmost South America and northeastern South America, what is it doing under orbital scale, and in the orbital time scale. So unfortunately, so far we do not have long records, neither from land nor from the ocean, at least not for places to the south of the equator. We are working on this to get longer records here, but so far I'm showing you a 5,000 years long record only. Yes, I know this is not much to see orbital scale changes, but this is what is available and is not impacted by sea level changes, because some of the records here are strongly controlled by sea level changes, and we don't want to see sea level changes or changes in siliciclastic input that are rather controlled by changes in sea level. We want to see continental signals, changes in precip. All right, so in this specific place, this is a core collected around 4 or 5 degrees south. I want to highlight you the black record. This is titanium calcium ratio again, and for the last 5,000 years only. But we have a beautiful signal, and this signal points to decreased precipitation when we go from the mid to the late Holocene. This is corroborated by a stalagmite in green, this record here, very close by. So both of them show decrease in precip from the mid to the late Holocene. Other marine records in the neighborhood of this other one with much lower temporal resolution show the same feature. And what is interesting is that a record northernmost South America, the classic Cariaco Basin, show a similar decrease in precipitation. This is only titanium, as you know. Classic record from Cariaco shows a decrease in precipitation from the mid to the late Holocene. But just to refresh your memory, from the mid to the late Holocene, for say Southern Hemisphere summer or autumn, take March as example. For 10 South, what we have is an increase in insolation. And how is it possible that we have an increase in insolation, but we have a decrease in precip all over the areas affected by the intertropical convergence zone if westernmost Amazon and the South Atlantic convergence zone show the opposite situation? So in order to investigate that, we went into the FGOES S2 fully coupled climate model, and I'll show you 2 model outputs, okay? First, I'll show you this plot here. This plot shows maximum precipitation zonally integrated from this latitudinal interval from 20 north to 20 south. And what I'm showing here is first, mid-Holocene values in the solid lines, so in red and blue. And in the dashed lines, I'm showing you late Holocene values. And why I do have 2 curves for mid-Holocene, 2 curves for late Holocene, that's because I'm considering the time window, March to April, in red. Remember, this is when ITCZ is located furthest south over northeastern South America. And in blue, I'm showing August to September. That's when ITCZ is located furthest north over northeastern South America. And what you will see is that both curves, if compared to the dashed curves, they are farthest away from the equator. And so this means that when we move from the mid-Holocene to the late Holocene, there is a contraction in the peak of precipitation. This hints that periods of higher austral summer insolation, for instance, the late Holocene in comparison to the mid-Holocene, are related to a contraction of the seasonal migration range of the intertropical convergence zone, at least over northeastern South America. Please consider that this does not negate the classic Cariaco Basin record. It only shows that the suggested southward migration of the ITCZ didn't happen, at least over southeastern South America, because what actually happened was a contraction of the intertropical convergence zone. And the reason for this contraction is the response, the sea surface, the changes in the gradient and the interhemispheric gradient in sea surface temperatures. And I can go into more detail on this if necessary. But For the moment, I will skip to a second model output that points us to another mechanism that was also relevant to explain these changes in tropical South American precipitation, and namely, and more specifically in this region, that is strongly affected by the intertropical convergence zone. And here I'm showing a mid-Holocene minus late Holocene, so an anomaly of velocity potential and divergent wind component for this box here, for the lower troposphere. And what we can see is a clear anomalous convergence here over the equatorial Atlantic, Western equatorial Atlantic, extending over Northeastern South America in the lower troposphere, okay, during the mid-Holocene in relation to the late Holocene. And this occurs because a weakening of the Nordeste low. Nordeste low is a feature sitting in the upper troposphere over this same region here. That is in turn linked to a weakening of deep convectioning happening over Western Amazonia and the South Atlantic convergence zone during the mid-Holocene. Indeed, the mid-Holocene was relatively dry in the Western Amazon and the whole South Atlantic convergence zone. And there is a regional Walker circulation with updraft over the Western Amazon and subsidence happening over northeastern Brazil. When we now go to the normal development of time, there is from mid-Holocene to the late Holocene, we see that high austral summer insolation also intensifies the regional Walker circulation, producing or bringing more moisture to Western Amazon and the South Atlantic convergence zone and less moisture to northeastern Brazil. So both processes acted together and helped each other in order to produce a drier northeastern Brazil, if you want, a drier Cariaco Basin from the mid to the late Holocene. All right. And if we now depart for a short while from purely precipitation phenomena and records over tropical South America, and we'll look a little bit into how did Amazonian biota respond to those, I'd like to show the last glacial maximum, because last glacial maximum was extremely important in Amazonia. You may have heard very large discussions about biodiversity development in Amazonia. And there are many theories out there in the literature, and some of them call for major changes during many glacials, not only the last glacial maximum for sure, there are many glacials over Amazonia. And so let's see how what can we learn for biome changes in Amazonia based on the precip changes we just reconstructed. So what I'm showing to you here is outputs only for Brazil, okay, not the whole South America, of a potential vegetation model, okay, potential vegetation model forced by LGM conditions. And these LGM conditions were taken from CMIP5. So CMIP5 ensemble was used here to force a potential vegetation model, and we used LGM concentration of greenhouse gases as well. This potential vegetation model has 6 biomes, and as you can see here, dark green tropical evergreen forest, light green tropical seasonal forest, and so on, all the way to semi-desert in brown, light brown. And we have 2 plots here. Here's how is the present simulation of the model. It's going a fairly good job when compared to pre-industrial vegetation or pre-colonial vegetation, if you want, over Brazil, because there was a lot of change in colonial times in Brazilian vegetation, at least in the coastline. All right. And here we are showing a LGM scenario, -4C, if you want. And I'd like you to focus on eastern Amazon. And over the eastern Amazon, we can see a progression of tropical seasonal forest over tropical evergreen forest. But it's not that large, but there is a progression. There is an intrusion of seasonal forest against tropical evergreen forest. But when we look to central and western Amazon, there was no big change, at least in this model. And in order to understand this, oh yeah, and more importantly, is that LGM simulation is supported by a very extensive compilation of paleo records, all right? And here we run sensitivity experiments on the same vegetation model, potential vegetation model. Here we are showing only the influence of CO2, left-hand side at the center, only the influence of changes in precip, LGM, okay, in relation to molder. And here we are showing the effect of changes in temperature, okay? All right, so what we can see is when we decrease CO2, we have a massive change in tropical evergreen forest to tropical seasonal forest. When we change precipitation, and basically what is the change in precipitation is there is a Eastern Amazon decrease in precipitation and a Western Amazon increase in precipitation during the LGM, and this is supported by the results I just showed you before. We see there is some change, but not as large as the change in CO2, the change triggered by the change in CO2. But when we decrease LGM temperatures, apply this to the model, there's a counterbalance. There's an expansion of tropical evergreen forest. So the results we see here is obviously a interplay between changes in CO2, precip, and temperature, so that a decrease in precipitation and CO2 triggers this advance of tropical seasonal forest and a little bit of savanna over evergreen forest in the eastern portion of Amazonia. But western and central Amazonia remained largely unchanged during the LGM, mainly due to the negative temperature anomaly. So this is very important. All right, so this is it for the orbital scale changes, and now we go for millennial scale changes. And to start with millennial scale changes, I'll show you data from a core collected at 4 South. And for this core, we have all these panels here, exception made of the orange curve at panel A. But all other data come from the same core here. This core only covers the last 25,000 years, because obviously here we are interested on the last deglaciation. We have the last glacial maximum here. We have Heinrich Stadium 1 and the Younger Dryas, 2 periods of marked millennial scale changes over global climate. This is AGES-1 for short, and this is the Younger Dryas. In our record in black, we analyzed the protactinium-thorium ratio, a good proxy for the strength of the AMOC, and we see what has already been shown for Bermuda Rise and other places in the North Atlantic is the decrease in the strength of the AMOC as we enter into AGES-1. AMOC stays very weak or even collapsed, if you want, during part of AGES-1, and an increase in the strength of the AMOC after the event in the transition to the bowling alley. Now, I want to focus your attention on panel B, and this is deuterium isotope of plant waxes. So we have here a proxy for continental precipitation, because these plant waxes are produced by continental vegetation, and the more negative the deuterium isotopic values, the higher the precipitation on land. In this relatively small drainage basin called Parnaíba drainage basin. And what we can see is a major increase in precipitation during Heinrich Stadium 1. And again, not that strong, but also an increase during the Younger Dryas. During these same 2 periods, in terms of linear sedimentation rates, we have major changes. We are going from 10 to 20 in blue here, sedimentation rates during the LGM. Please consider we had 120, 130 meters lower sea level, and sedimentation rates were 10 to 20 centimeters per 1,000 a year, similar to early Holocene and mid Holocene values. But when we go into AGES-1, we go up to 100, 120, 150 centimeters per 1,000 a year of sedimentation rates. And then sedimentation rates decrease dramatically during the bowling alley road. It raise again a little bit, not that much during the Younger Dryas, and decrease again during the early Holocene. And what triggered this increase in sedimentation rate? This is not primary productivity, because this is an oligotrophic area. This is basically the discharge of siliciclastic sediments from this not that large drainage basin, but that suffered torrential and a major increase in precipitation. There are continental erosional features on this portion of semi-arid northeastern Brazil that are hard to believe that non-perennial rivers today could have ever been able to erode. We are dating these features, and we hope to come up with a nice publication on this as well in the near-term future. Okay, and this increase in siliciclastic discharge is shown here by the iron to calcium ratio. You see major increase in the orange area at the panel C here, and decrease bowling alley, decrease again Younger Dryas. All right, if we but plot our delta D data, the same data I showed you before, but only for the interval from the LGM to the end of AGES1. So here's the dots are color coded. Okay, so very light blue here is LGM. As you can see, AMOC is still strong. And as we advance to a more deeper blue here on your left-hand side, we are going into AGES1 and into the very end of AGES1 around 14.9 thousand years before the present. This is 200-300 years before the overshoot of the AMOC that happened at the transition from AGES1 to the bowling alley. And what we are plotting together with our delta D data is the interhemispheric sea surface temperature anomaly reconstructed, okay, from Chacun and co-authors 2012. Here we're showing North Atlantic minus South Atlantic reconstructed temperature difference. And we see this beautiful linear and synchronous changes in precipitation over northeast Brazil and the Atlantic interhemispheric sea surface temperature gradient. And the temperature gradient was controlled by AMOC strength. This is due to the bipolar thermal seesaw. And as the South Atlantic warms in relation to the North Atlantic, the intertropical convergence zone migrates to the south in a linear and synchronous way. This was what we were able to show on that publication. But now expanding a little bit the time scale and also expanding the geographic coverage of the records, I'd like to show you 3 marine cores or records from 3 marine cores, namely Cariaco Basin in blue, a core under the influence of the Amazon mouth in, excuse me, this is green. Yes, sorry. So Cariaco Basin in green, Amazon in blue, and northeastern Brazil in black. In between, we have a cave record, very well dated cave record from westernmost Amazon. This is gray. We only have here 40,000 years before the present to 29,000 years before the present. So it's a window within the last glacial. Within this window, we have 2 Heinrich stadials, so periods of a strong decrease in strength of the AMOC. Ages 3 in the pink vertical bar here, and ages 4, again, pink vertical bar here. I'm showing Northern Grip, Delta 18 just as a reference. All 4 records here are organized in such a way that they show increased precipitation upwards in the plot. So beautiful, high resolution, well-dated Cariaco record show decreases of precip during Heinrich stadials, but also during Dansgaard-Oeschger stadials 5 to 8. They are characterized by the light blue vertical bars. When we go now to the Amazon, although the core was collected 6 north, but the core is recording information integrated from the Amazon basin, and most of the Amazon basin is sitting to the south of the equator. What we see is a increase in precip again over ages 4 and ages 3 in opposition to Cariaco Basin, and also an increase in all of these 4 Dansgaard-Oeschger events. Please keep in mind that Cariaco Basin, we see decrease in precip. Here we see increase in precip. Interestingly, when we look further southeast, so a record of northeastern Brazil, this is Amazon, this is northeastern Brazil, so this is northeastern Brazil, this is Amazon. We only see increase in precip during ages 4 and ages 3, with very little or even no change during Dansgaard-Oeschger stadials. I would like to raise, so we see opposition between northernmost South America and South America, tropical South America to the south of the Atlantic. And what is important is that this record here from the westernmost Amazon, that is Pacupahuain Cave Delta 18O, very well dated record, show a beautiful and a lot of features during this time interval from 40K to 29K before the present. And our record of the Amazon mouth, more than 2,500 kilometers apart from Western Amazon, show very similar and short-term variations. So this allows us to mention that there is a quick transmission of Western Amazonian climate signals all the way this transcontinental basin to the Atlantic, and that Dansgaard-Oeschger stadials produced strong shifts in the northern edge of the intertropical convergence zone, Cariaco Basin, for instance, and also over westernmost Amazon, cave record and Amazonian record, but only weak or none or no changes over northeastern Brazil. There is the southernmost reaches of the intertropical convergence zone. All right, for the millennial scale, we can so far mention that there was a southward migration of the intertropical convergence zone during events of a weak Atlantic meridional overturning circulation. But I would like to show you how far south these positive precipitation anomalies occurred over South America. Therefore, we compiled many records over marine records all the way from 10 north, Cariaco Basin, to 32 south. This is Rio Grande Cone. Rio Grande Cone is not Rio Grande Rise. This is Rio Grande Cone, another feature, bathymetric feature, important feature in the Argentine basin. And there are a lot of details here. I'll not ask you to look into detail into this figure because I'll drive you through it. And I consider this will be an easy go if we consider that precip in all records increase upwards. I even had to break this plot in two because of the many records. We have time going from 75,000 years before the present in the right to the present and in your left-hand side. And if we start with Cariaco and Tobago Basin, so both to the north of the Atlantic, we see negative precipitation anomalies during Heinrich stadials. And I'll take AGS1 here as an example, okay? But then when we go to the Amazon, the record I showed you before, we see positive precip anomaly. We are to the south of the equator. And when we make progress all the way now through all these records to 10 south in this record here, we see a similar feature, increase in precipitation during all Heinrich stadials of the last 75,000 years. But when we look to the next record going south, there is a record at 20 south, and then both records, the south of it, I'm plotting the best records available here, okay? 27 south and 32 south, the millennial scale signals disappear. And millennial scale signals disappear because most probably there was no substantial changes in precipitation over subtropical South America during the last 75,000 years. Yeah, all records here are based on XRF information, apart from a reflectance of the Cariaco and lightness of the Tobago Basin record. And many of them titanium calcium, some of them iron to calcium ratio. So very similar proxy applied in this many records. All right, but what could be the reason for this change in anomalies, millennial scale anomalies in precipitation over tropical South America? In order to investigate the possible causes of that, we run Earth System model, ECSM, and CESM, more specifically. And I'm showing to you here the AGS1 minus LGM precipitation anomaly for different watersheds, for different drainage basins in tropical and subtropical South America. We are going all the way from the Amazon to the Parnaíba, to the San Francisco, and then two small drainage basins Doce, and Itajaí. And then the big subtropical, the second largest drainage basin in the continent, the La Plata drainage basin. What we can see is a positive precipitation anomaly. By the way, we are showing here monthly changes, HSM minus LGM. Okay, so we see positive precipitation anomalies during HS1 in relation to LGM in the Amazon. We see positive precipitation anomaly over the Parnaíba. We see positive precipitation anomaly over the São Francisco, as shown by our compilation of marine records. And similarly to the lack of millennial scale probability in our records that I just showed you before, last slide, we see no major changes in precipitation anomaly in these three drainage basins that are either at the very southernmost portion of tropical South America or in subtropical South America. So there's no substantial positive precipitation anomaly over subtropical South America, but obviously a major change in tropical South America. Importantly, the positive precipitation anomaly over the Amazon doesn't occur during austral summer. That will be December, January, February. Actually, we see a negative precipitation anomaly, but the positive precipitation anomaly occurs during winter and spring. And this is at odds to the basic expectation of a general strengthening of the South American monsoon system during, or summer monsoon here, I should say, during millennial scale events. And well, by looking into the details of the model, we see that it is dynamic and thermodynamic processes that are responsible for these changes. And we cannot simplify the situation by explaining changes in millennial scale precipitation over tropical South America as a simple strengthening of the South American monsoon, because it actually doesn't get stronger, as you can see here on this plot. Good. And to finalize, I'll show you just one slide about how did the Amazonian biota respond to Heinrich Stadia 1. So I'm coming back to Amazonia. I'm coming back to the biotic response to changes in precipitation, to depart a little bit from only precip records. And here I'll show you data, mainly this green record here. This is delta 13C in long chain N alkanes. This is a good proxy for the photosynthetic pathway of the major portion of the vegetation, where in the Amazon, because this record comes from a core collected under the influence of the Amazon River. And what we see here, we have time for only the last deglaciation from 20,000 years before the present to 10. We have HS1 in the two gray bars. We split it in two because we see two phases in HS1. We see a first phase where there is no major change in the photosynthetic pathway of vegetation over the Amazon basin. Well, okay, C3 will be most trees, and C4 will be most grasses. Not most, but larger fraction of grasses, and here a large domination of trees over the Amazon. Okay, and in this first phase of HS1, we see lower, please note the inverted scale here, lower calcium to iron ratio in the same core. So there's a lot of terrestrial sediment input, and this high sediment input is most probably related to increased Andean precipitation in the first phase of HS1. And as we transition from the first to the second phase of HS1, this is a cave record from westernmost Amazon. And we see a decrease in precipitation over the Western Amazon. We don't see generation of sediments anymore that strong. But what we see is a shift, or a larger fraction of C4 vegetation over the Amazon. Obviously, this is not the whole Amazon by far. This is a intrusion of savanna over rainforest. And this most probably happened over northernmost Amazonia as the tropical rain belt shifts furthest south, as also suggested here by the very low terrestrial input over Cariaco Basin. So we have the red record coming, the red high resolution record coming here from the Cariaco Basin. All right, so now back to the takeaway messages. These are the very same I showed you before, and I would like to quickly go through them, and I will read them again, but I think they are relevant. That's the reason I will read together with you. So high austral summer insolation enhances convection and precipitation over Western Amazonia and the South Atlantic convergence. First. Second, it also triggers a contraction of the seasonal migration range of the intertropical convergence zone. Precipitation over northeastern Brazil that is strongly controlled by the intertropical convergence zone varied linearly and synchronously to past millennial scale changes in the Atlantic meridional heat transport and AMOC strength, if you will. And that we see no substantial positive precipitation anomalies during higher stages over tropical South America. With this, I'd like to thank you very much for your attention.
Thank you very much, Cristiano. And now let's see if there are any questions. If you'd like to raise your hand or put a message into the chat, please go ahead. Cristiano, maybe I could start things by asking you, so what do you think is missing from the study of the paleoclimate over the last sort of few glacial cycles? If you were allowed to collect a new core somewhere, or where would you choose? Where do you think the record is least well developed? In the Northeast?
Okay, I would definitely go for the last, say, 300,000 years or 500,000 years over northeastern off northeastern South America, not
right.
Cariaco Basin,
No.
because we do have information, but to the south of it. Obviously, a record from the Amazon would be most welcome, because we have, you have seen what we have in high temporal resolution. I mean, high temporal resolution is very subjective here, right? High temporal resolution for one is not high temporal resolution for the other, but we lack, in my opinion, a record for the Amazon and also for northeastern Brazil, covering the last, say, 3-4 glacial cycles in high temporal resolution. This would be a must and a short-term aim.
Right. Presumably the Amazon margin drilling would be a bonus if we can make that work.
Yes, very much. If that would work, it would be fantastic. The Amazon will be nicely covered because the quaternary package that will be drilled, that hopefully will be drilled by the JR, that's Expedition 387, right? The quaternary package is very thick. So yes, we may potentially have a nice, very nice record for the last 500,000 year, even longer actually, for the Amazon.
Right. Thank you. Would anyone else like to ask a question? Stunned them. Well, okay. Well, here we go. Dylan, would you like to? Why don't you unmute yourself and ask your question?
Hey there. Yeah, that was a great talk. So I just had a question about the contraction of the ITCZ over the last 5,000 years that you're talking about. So for the Paraíso cave record in the Eastern Amazon, there's also kind of an inferred decrease in precipitation. And so with the contraction that you're talking about, you're suggesting that not only is it not moving position, but is there any sort of change in intensity that you're thinking as well? Like, is it not bringing as much moisture into the continent? Okay, that's good question, Dylan. Although I don't have yet the necessary records to give a strong support to what I would say, so it's a hypothesis, okay? But if I consider that the ITCZ is not covering anymore a large latitudinal band, but is contracted and migrating within a much narrower latitudinal range, I can only imagine
that the strength would be enhanced. And I will point out, I'm not sure if I answered the question, but if you allow me, just another comment, and this links also to Peter's question, is the place that I would like to go, and that will be the smoking gun of the suggestion of a contraction of the ITCZ, would be to a site, please correct me if you disagree, okay? But would be to a site at, say, roughly speaking, 2, 3, 5 degrees north, so close to the equator, but slightly to the north, over the continent, where we do not have an influence of, say, the Amazon River, because the Amazon River brings signals from the Andes and may influence lowland records through floodings and droughts a lot. But if we find a record, high temporal resolution, close to the coast, because I don't want to go in deep into the continent to see a pure ITCZ or ITCZ, sorry, signal. But say French Guiana, for instance, is the small country. Not sure if you have in mind, French Guiana is a small country to the north of Brazil, placed roughly 5 north or so. That will be the place to go if we find a nice record there. There could be the smoking gun of this contraction, because there we should see an increase in precip. We see the decrease in precip Cariaco. We see decrease in precip over the Orinoco, even though the Orinoco is a large basin, but there is a decrease in precip integrated over the Orinoco. But I agree this is not a good record for the ITCZ, because it's a large basin draining all the way to the Venezuelan Andes, and it's different processes as well. Decrease in precip over northeastern Brazil, pretty clear, I would say, but the smoking gun is missing.
And so you're thinking, oh, sorry.
Follow up. Right.
Yeah, so you're thinking that the Paraiso Cave record is not showing like an ITCZ, like a reflection of ITCZ strength, or?
Well, I think Parisi, yeah, I think it's a good record, but yes, but I'll like to have at least another record in order to have a more robust with a, if possible, with a little expanded time window. We are working to expand the time window over northeastern Brazil in order to have, say, at least 100,000 years or even more, that is not affected by sea level, because this is the problem. We have cores there published, but titanium calcium, for instance, is strongly impacted by changes in sea level in the orbital scale. In the millennial scale is very beautiful, but the orbital scale, there is this strong control of sea level. So longer record.
So, Steffi, do you want to ask your question? You want to unmute yourself? I'll ask Steffi's question for her because her microphone is not working. She says, you showed many marine records extracted from cores. How much of a problem are ocean currents in destroying or diluting information coming from the land?
Very good point, Steffi. Very good point, because I would add, just to make things more complicated, I will add to your question that I will address for sure, another complicating factor related to marine cores, namely when we are looking to large drainage basins, where is actually the signals coming from, right? The Amazon is a very large drainage basin, as you all know, the largest. And so at the end, you may question, and there are different climatic patterns over this basin, north, south, east, west, and you may ask, well, where's material coming from? We have different proxies. Are different proxies representing the same region or not? So marine cores have advantages and disadvantages. So first to your question, and then I will say a few words about these how to sectorize, let's say, big drainage basins like the Amazon. Yeah, your question, if marine currents could dilute or complicate the signals. I would say that if we do have large drainage basins upstream a certain marine current, okay, then the information we have from a specific core may be changed by actually information coming the neighbor drainage basin. So both drainage basins deliver sediments to the ocean, and then a certain marine current transports sediments, say, along the slope from the mouth of one major river to the mouth of another major river. And so this may be an issue. But in the case of the drainage basins I showed, namely the Amazon, Parnaíba, São Francisco, Doce, Itajaí, and Plata, they are either the largest by far, like Amazon and the Plata, in their respective regions, or they are, regionally speaking, the largest drainage basins. So there is not big a role of currents, let's say, transporting a substantial amount of sediments at these depths. When we go to the very deep ocean, to the abyssal plains, then for sure we have very low sedimentation rates, very fine-grained siliciclastic sediments, and long distance transport. So we see clay minerals from far away being transported thousands of kilometers. But in the slope, where sedimentation rates are relatively high, 10, 20 centimeters per 1,000 years, we assume, and not only assume, that we have kind of the signals of the respective drainage basins without much, let's say, dilution by currents. Importantly, we use proxies like neodymium isotopes, strontium isotopes, and lead isotopes in the siliciclastic fraction to pinpoint sources in the continent. These isotopes allow us to differentiate different drainage basins, but also, and now I come to the point I raised on top of your question, sectors within the same drainage basin. Take the two largest drainage basins in South America, for instance, the Amazon and La Plata. They have very different, for instance, neodymium signatures because of the Andes and the lowlands with cratonic or Paleo-Mesozoic sediments derived from cratonic rocks. Okay, so they have very clear signatures in terms of epsilon neodymium and strontium isotopes that allow us to differentiate between different sources within the basins. This is why we are able to say, for instance, that by far the largest fraction, and this was clear already for decades, right? That the largest fraction of Amazon terrigenous sediments delivered to the ocean come from the Andes, from the eastern Andes. Madeira and Solimões, these two rivers, they deliver by far the largest fraction, and the lowlands deliver a substantial but smaller fraction of sediments.
Okay, we have another question from Melissa. Do you want to ask your question?
Hi, Cristiano. Thank you very much. I just wonder if these other convective systems that you talk about, the South Atlantic Convergence Zone and the Nordeste High, migrate just like the ITCC did in the past.
I am, Melissa, are you done? I'm afraid I am afraid I didn't got the question. You mentioned the South Atlantic Convergence Zone and the ITC, but I'm afraid I didn't got the question. I'm sorry for that. I'm sorry, but could you please put it?
Yes, of course. I just wonder if the South Atlantic Convergence Zone or the Nordeste High also migrate in the space, you know, like the ITCC.
Wow. Well, excellent question. Excellent question. My God. And I'm afraid, well, this is very good question. We believe that the South Atlantic Convergence Zone migrates, but not too much. Okay, for short, in order to the short version of the answer is this: the South Atlantic Convergence Zone seems to be much more stable in terms of its position than the Intertropical Convergence Zone. We have support for this statement coming from model experiments. We have support for this statement coming from instrumental data, but obviously we have to take care here because obviously instrumental data covers only a small fraction of the scenarios and variability that we have in geological record, and it's really a short, narrow window. But in this narrow window, we see the South Atlantic Convergence Zone as a much more stable feature than the Intertropical Convergence Zone. But still, there seems to be some migration on the position of this specific feature, not as large as ITCs. Okay, this is my answer. Regarding the Nordeste High, very good point. And here, the Nordeste High shows a seasonal migration of its, let's say, position or strength and position, right? But I have to be honest that for the Nordeste High, I cannot give you an answer today. Very good point. Very good point. I'll take note here, and I'll try to see in my records and also in the literature if I find an answer. If you have a clue, please tell us.
Cristiano, we have one more question from YouTube, from a Vinicius Mendez, and he's asking, how similar are the high solar insolation periods? How similar do you think they are to a future global warming scenario?
Okay. Well, okay. They are different. They are different. The high CO2 under projection of CO2 by 2100, yeah, the end of the century, will make things substantially different from high austral summer insolation. I understand this is what the question relates to, and also very important to keep in mind is that we had high austral summer insolation. We now have a period of high austral summer insolation. Late Holocene is a period of high austral summer insolation, but we have recurring periods of high austral summer insolation during the last glacial and during previous glacials as well. And albedo was substantially different during the glacial, and also greenhouse gases concentration and topography over North America and Asia, and well, basically Eurasia was also very different because of ice sheets. And so this produced situations that were substantially substantially different from the future. Nevertheless, my opinion is that with due care, we can learn from the past to inform the future, either by validating models or by understanding the response and the feedbacks of different sectors, different components of the climate system, or by understanding the many flavors of the climate system to substantially different boundary conditions. Not to say, obviously, to understand in more detail climate sensitivity and constrain climate sensitivity, a key feature for future projections.
Thank you very much. So I think maybe, especially given the time, we should wrap this up. Maybe you'd like to join me on camera, giving thanks to Cristiano, or you can show your reaction, clapping with your emojis. But thank you very much, Cristiano. I would say, if you all would like to come back next week, it's going to be on the other schedule, and we're going to hear from Yoshimi Kuboto from Tokyo, and she's going to talk to us about millennial scale reconstructions and proxies in the East Asian monsoon. So come back or tune in next week, and stay safe, stay healthy, and enjoy the monsoon. Thank you.
Thank you. Bye.
Bye-bye.